Good afternoon. First of all, I have some notes just here. Nothing better than a good old handwritten backup notes. And I'm just gonna be reading from them bit by bit. So first off, good afternoon. My name is Javier Martínez, and today I will be sharing my work with you in theoretical parapsychology. We will build up to two big ideas by applying principles of physics to the study of mind-matter interactions. And I hope that this work will help shed some more light on the physics behind these mechanisms and serve as a groundwork for a method of boosting psychokinetic effects caused by subjects in the lab. That would be our outline for the remainder of this presentation. So, psi operations are special cases in nature that involve strange action at a distance, interaction to either obtain information in the case of precognition, or change the odds of an event to happen in the case of PK. Helmut Schmidt proposed that these changes are only possible if we interpret these kinds of phenomena as a kind of, communication process between the physical system and the mind of the subject. And by doing so, he conjectured a bridge between information theory and parapsychology. Well, the way this mind-matter communication channel is introduced in parapsychology is very hand-wavy, and we have failed to come up with experiments to measure its properties, such as, its geometry, its existence, and even its constituents, which would be actually the harder of the three, in a direct manner by probing space-time. So we should at least focus on proving its existence and find a way to prove it. Find a way that should exist as a natural consequence of known laws of nature. To take this route, I focused on studying the phenomena through the lens of thermodynamics, as the concept of entropy is one shared between itself and information theory. Entropy is a concept cherished and loved by both, and it is defined in pretty much the same way, except thermodynamics, it gives it units of energy over temperature, but there's really not that much different. It is essentially a measure of randomness, and the more entropy a system has, the less predictably it will behave. This boils down to saying that the probability distribution for the states of a system will become more spread out when the system has more entropy, as is the case in this graph. Using the definition of entropy, we can parameterize the evolution of the distribution with time to be able to measure how entropy changes. For example, we can measure how entropy changes between time points, as is the case with this second example. Or we could measure changes between the observed distribution and the one predicted by theory without PK influence. Of course, if the design system for our PK experiment is at equilibrium without psi influence, then this 1H theo will just be a sort of a constant if we just consider random expected noise from the environment. Predictable noise from the environment. Now, it is immediately obvious that when a participant is successful in increasing the chance of a particular event, entropy must decrease in our design system, and the uncertainty is diminished. This in turn breaks the second law of thermodynamics at first glance, which says that entropy tends to increase for an isolated system. So this HM, is immediately recognizable as the entropy lacking in the system, in our design system. But to move forward, we need only ask one question, which is our system really isolated? And the reason for this is that the only way entropy can decrease in a system if it is really only a subsystem of a larger one. For example, when you leave a block of ice to melt on a table, while the entropy of the table goes down as it cools off a little, the entropy of the ice goes up as it liquefies. And the sum of these changes in entropy is a net positive. Together, they will make the isolated system. Well, of course, if we neglect effects coming from air surrounding the ice and all that, if we just take the table and the block of ice. Now, if the second law is true, which for now, let's assume that it is, there has to be an additional system in contact with the one that we built in the lab in order to compensate the entropy lost in it. Together, they'll make the isolated system where the second law holds. Moreover, since we observe a correlation between the intent of the participant and changes for the odds in the system we built, and these changes were caused by changes in the unknown system, then the unknown system relays information from the brain to the other system. This is effectively the communication channel we were looking for. Its existence only depends on the fact that the second law of thermodynamics holds in general, and the person would effectively send messages through this channel during PK, and possibly other kinds of anomalous interactions. Now let's keep going, because that was the first important point. Now the second one. For the second part of this presentation, we are going to concern ourselves with what we can know and improve about this information transfer process. Distributions obtained by most, if not all, of PK experiments are constructed by keeping track of all events throughout an experimental trial. So that means that the distribution we end up with would be sort of a mix and match situation, taking bits and pieces of how the actual probability distribution changes over time as a consequence of the aforementioned messages traveling through the channel. And while we would like for an experiment to be able to come up with the actual distribution at each point in time, and these can be easily achieved by taking a large number of trials in short time spans, so that together we can generate a distribution at each point in time and let them evolve. So something like the second image over there. We would expect small fluctuations in any system that can be due to predictable physical noise, as I mentioned earlier. But when these are filtered out, we have no choice but to identify the fluctuations in probability as the ones produced by the messages being sent. The types of noise in these sort of processes can be divided as follows. They can be either noise attributed to the participant tasked with influencing the system, which I would consider to be internal noise, and the two others which would be sort of external noise. One would be having to do with the actual channel itself, and another one would be the noise attributed to the decodification process between the unknown channel and the physical system. The last two can be even considered constant in a good lab setting, because we would not expect any directed messages, and I'm going to say directed messages in quotes, coming in, like, for example, an outsider applying their intention to the design system to sway chance one way or the other. This would be an example of non-negligible background noise fluctuations coming from the channel, not having to do with how the actual system is going to be decodifying the message. And if the external noise is constant, then the rate of change of the distribution must then be a function of whatever the main experimental subject's mind is sending through the channel. So the evolution of a probability distribution with time in general is given by a differential equation, which is called the Fokker-Planck equation, which is over there now. And the terms d and mu are the diffusion, which is that one, and the drift term, which basically model how the distribution spreads out and changes its mean as time goes on. These are what motivate the evolution of probabilities through time. And following this train of thought, then, well, changes in diffusion and drift over time must be functions of changes in informational content sent. And if the informational content sent is directly linked to neural activity, then the functions must be of changes in neural activity. For starters, we could suggest that rates of change for diffusion and drift in a particular state can be obtained from a linear combination of the total time derivatives of the functions which measure the neural activity for each region of the brain involved in directed intention processes towards one particular state. One possible collection of these functions could be voltage versus time readings for two faraway electrodes when the outcomes of an event are registered in very different parts of the brain. So, at last, for this second part of the presentation, we propose the following experimental protocol. So, let us see. First, we could measure the wandering probability distribution for a given micro PK experiment. I made a mistake there. It shouldn't be, in general, just PK. And then we could feed into the Fokker-Planck equation to get drift and diffusion, and then find the coefficients that best fit the EEG linear combination hypotheses. Of course, it could just be that it's not a linear combination and it's another combination of functions, but it seems like a good first try. So by doing so and applying this method to a great number of participants, we would be able to pinpoint specific local neural behavior that correlates to higher efficiency with low variance and expected values closer and closer to the event the participants sent out to manifest at the start of their trial. And I hope that all of this benefits experimental parapsychologists, and I thank you all for your attention. I know this is very heavy in theory, but yeah.
We have a lot of time for questions, actually. Yes.
Thank you very much. I like this approach, but this is a thermodynamic analysis, basically.
Yeah.
And like the thermodynamics is in ordinary physics derived from like the Boltzmann equation, and microphysical can be derived from microphysics at the very base. Have you thought about taking it that far as to what is going on at the microphysical level?
Well, we would have to consider to do that, we would have to better explore what the unknown system would be doing and how it is composed. So that would require experimental data, which I don't have access to.
But you can also approach it theoretically, too.
Like if I just come up with an ensemble and see how that changes, that would be, yeah, I could try and do that. Thank you.
Any other question?
Yeah, I see a reference to Rupert Sheldrake's, I guess one of his most famous hypotheses. How does that connect with what you're?
Well, because in my personal belief, the morphic hypothesis, the morphic field that he proposes is essentially a channel of communication transfer between emitter and receiver pairs. Yeah.
That's an example of the microphysical theory connected.
Any more questions? Any more questions?
Hey, Javier.
Of course, yeah.
I wasn't sure I understood. You were saying the noise from the internal representation, the internal system, was different than the noise from the external system.
Yeah.
I didn't understand why you were kind of dismissing the external noise.
Well, I'm not dismissing it. I'm just assuming it's going to be constant in a sort of quote-unquote good lab setting, because then good lab setting for this particular kind of experiment. Because if you consider that the majority of the changes that are going to be being made on the actual probability distributions are going to be directed by just the single participant in the experiment, and all the other observers that know of the experiment are going to be kept like taking notes and just recording data, then there isn't that much influence, or it should at least be constant over time, which, well, there can be a lot of influence, but it should be constant for the duration of the trial.
Right. Okay, I see your point. The reason I'm asking is because things like unconscious influence on electronic systems occurs all the time. And it can happen from the experimenters as well as the participants. And so I'm thinking there might be another variable in there somewhere.
Yeah, but if it's not constant, we can always change the equations a little bit and explore them further.
Okay.
Any more questions?
Any other?
I'm not sure I totally understood the experiments with EEG. So is the idea to measure the drift of the micro-PK system, yeah, and then the entropy in the EEG? Is that the idea? Could you clarify and like, because I didn't understand that?
Yeah,
that's
so
really quite interesting.
The idea would be just taking the drift and the diffusion terms of the equations and see that if they vary in time, try and correlate that to how the EEG readings of a particular state and the person that is trying to influence the system behave for one state or another one. And the distribution, if it's a system that has only two states, for example, a coin flip, which might be a bit reductionist, but if it's something like that, then maybe we could keep track of them. But they have to be sufficiently far away so that the readings can be done efficiently.
Okay. And would it work if you don't use a PK system but just an action? Does that make sense? So if you press a button and you do a coin, it's like if you reduce entropy by action, would this formalism function as well, rather than using PK? A way to validate the way you do your formalism.
I hadn't thought of that, but that's also a good suggestion.
Okay. Any other questions? No questions? All right. Well, thank you very much, Javier.